Hi, I'm Alex Phelps,
I'm Isaac Little.
Hi, I'm Jeremy Manus.
and we're Team 26. This is our final project for CSC 591, Deep Learning and Neural Networks, and it is about recognizing the American Sign Language alphabet. All right, without further ado, let's get started. American Sign Language is the fifth most used language in the United States, with reliable estimates of users ranging from 250,000 to 500,000 people. This is good because there are approximately 600,000 deaf people in the United States, or about 0.22% of the population, with about 6 million people reporting having a lot of trouble hearing. American Sign Language is a complete language, but the simplest form is called fingerspelling, or simply spelling out words with letters made by your hand. There are 26 letters in the alphabet, and these are in our training set plus 3 additional signs for delete, nothing, and space, making a total of 29 symbols to be categorized. We now know why sign language is so important, but we don't know what problem we're trying to solve. With sign language being so widespread, a tool that automatically recognizes it and can read it would be invaluable to those hard of hearing, those hard of sight, as well as people who don't know sign language at all. Such a tool would open up a new world of communication with those who are familiar with sign language. We decided to create a proof of concept project for recognizing sign language by recognizing fingerspelling first, which will create the basic building blocks of using temporal data and video to recognize full sign language.
All right, so obviously in order to do this, we're going to need a lot of different images of fingerspelled letters. So we looked around for our options and came across a Kaggle data set by a user named Akash. It contained 87,000 images in those 29 classes that Alex mentioned, and there were a lot of positives with this set. There were a lot of different angles, there were different lighting arrangements, and there were different signers, but they all appeared to be taken indoors, potentially even in the same room. And so we knew that that similarity between the images would lend itself to overfitting if we weren't careful. So while this made a great training set, we wanted a test set that featured the same classes but had some unique aspects. So we came across a different Kaggle data set generated by a user named Dan Razban. This data set contained 870 images in those same 29 classes and had more of the variety we were looking for. While there was one signer, there were a bunch of different backgrounds, both indoors and outdoors. You can see the complicated construction site background in the test set below compared to the rather simple room in the training set above. Next slide, please. So we decided to use a CNN for this problem due to their excellent suitability for image classification problems. Our first instinct was to make use of transfer learning. However, we found that while we got amazing results on the training set and we got those quickly, we performed pretty poorly on the test set. So after doing some research into other people who tackled problems like this, we found that often models that perform well were quite simple in design. One issue we would run into not infrequently would be that the model would quickly settle on predicting all the images in one class and then just doing some little overfitting. And because we had 29 images, that led to that 3.5% test accuracy you can see here for some models. Next slide, please. So we knew overfitting would be a big problem, and we also knew that a great way to reduce overfitting is applying transformations to your input images. We tested a couple different things, but we found that making brightness adjustments, as can be seen at the bottom here, really gave us the best generalization to our test set. A thought we had, because the skin color of the signer, the background shade of the room shouldn't matter that much, we figured using grayscale images or perhaps using edge detection like our baseline comparison did, that would give us the ideal outcome, but that actually really decreased our performance on the test set. Another interesting behavior we found was the yields image sizes were actually quite small. Obviously, the effect didn't continue forever, but we would reduce the pixel size down until about 48 by 48 pixels. That was what gave us optimal results. Next slide.
In our final model, the image input size was reduced from the baseline 64 by 64 pixels to 48 by 48 pixels with no Sobel edge detection pre-processing. There are 3 convolutional blocks, with each block consisting of 2 convolutional layers. And in the first layer, there are 64 filters with a 4-4 kernel and a stride of 1. The second layer is a dilated convolution with a stride of 2 and the same number of filters and kernel size as the preceding layer. RailDo was used between each layer. The number of filters in each convolutional block doubles from the preceding blocks, so 64, 128, 256. And between the convolutional blocks, there's a dropout layer of 0.5. Finally, the classifier consists of dense layers of 512 and 29 neurons with ReLU and softmax. Next slide. Our primary metrics were accuracy and F1 scores. Compared to the baseline model, our overall F1 scores increased from 0.41 to 0.46 with some notable instances. The letter S in the test set could not be classified very well by either model. The letters D and U were most classified much more accurately by our model compared to the baseline. However, this model did not classify the letter P as well as the baseline. Overall, the accuracy of this model was 48% compared to the baseline of 42%.
All right, next slide. So thank you guys all for listening. Here's some of the resources we used, and we hope you have a wonderful day.